an almost complex structure is a section J of this vector bundle homomorphisms of our tangent space, and that sits over X, such that J squared is minus the identity. And so what this means, if you're like me and you have kind of a hard time reading this Pom notation, what this means is that at each point, your map J gives you a linear map on your tangent space, such that when you square that map, you get minus the identity. And now, what's important to note here is that J is real. J is a real linear map. It's acting on a real vector space. So when we compute the eigenvalues of J, we can compute, and it's a computation that I encourage you to try. So the eigenvalues of J are plus or minus I. When you do the computation, you discover that these are the only possibilities for the eigenvalues. And because J is real linear, these eigenvalues have to come in complex conjugate pairs. So we have both as our eigenvalues, and this produces a splitting of our tangent space, our complexified tangent space, according to these eigenspaces. So let me write this down. So this is the eigenspace associated to I. This is the eigenspace associated to minus I. And this here is required because, again, our tangent space is real. We don't have a notion of what it means to multiply a complex number on a real vector space. So what we do is we just attach a copy of C to our tangent space, and that allows us to think of multiplication by a complex number in this setting. Okay, this also gives us a splitting of the cotangent space, or it produces a splitting of the cotangent space in the same way. And this extends to the graded algebra of forms. So for a K form, the space of K forms, we can now write this in terms of PQ forms. So this will split as a direct sum of over P plus K of PQ forms, such that the sum of P and Q is the total degree K, and we're taking this guy to be the wedge sum of this guy with itself, P times, and this guy with itself, Q times. So in this, for the rest of this talk, I'm going to be talking a lot about PQ forms. What I'm talking about are elements of this space. You have a K form, which decomposes according to these eigenspaces into a form that has P in this particular eigenspace and Q in this particular eigenspace. Okay. So I'm going to talk just a little bit about the metrics that we'll be working with. It's not as necessary to understand what's going on, but it is good to understand the notation, and also it's nice to learn things. So a Riemannian metric G assigns to each point in your manifold a positive, in M, positive definite inner product on the tangent space. So i.e.,
Question for clarification.
yeah.
The complexified tangent space is always, the dimension is always divisible by 4, correct? You're tensoring over R without any quotients, and the original vector space supported a J. So that had to be even dimensional, and then you've doubled the dimension, right?
I don't think so. I think there's more in the chat. Yes. Wait. I don't know. I don't think that you are really changing the dimension of this vector space. You're taking something which is at least 2-dimensional and you're tensoring it with something which is 1-dimensional, which will give you a 2-dimensional guy. Does that answer your question?
Oh, okay. So there is some sort of, you can bring scalars over the tensor. It's not strictly speaking tensoring over R.
Well, you can't bring I out.
Right, but there is some equivariance condition using J.
Yeah.
While we're going back, do you mind going over why one is I and one is minus I? Because my intuition, when I see it, I would think one would be like 1 and one would be I. So can you just talk a little bit more about that?
One would be, oh, yeah. So this goes back to the computation of what your eigenvalues are. And you can use this relationship to compute the possibilities. You find those possibilities are I and minus I. I don't want to get too into that because we do have a lot to cover.
Okay, that makes sense.
Okay.
It satisfies the polynomial x squared plus 1.
Yeah.
Quick thing to Taurus's question. Taurus, the rank is 4R, but it doesn't matter. You're interested in the complex rank, which is, or 2n rather than 4n.
I see.
Thank you. Okay, so back to talking about our metric. So Riemannian metric G assigns to each point in your manifold a sort of metric in the vector space sense. These, at each point, your tangent space is a vector space. You get a metric on that vector space with this metric. Okay. And now I'm going to write down what it means for a metric to be Hermitian. So G is Hermitian if at all points in your manifold and vectors zeta and eta in your tangent space, at that point, our almost complex structure acts as an isometry with respect to the metric. And you can also, on your own time, show that this is equivalent to the sense that we might already be used to thinking of a Hermitian inner product. Here we've defined it in terms of our almost complex structure, but you can play around with that and show that equivalence. So finally, I'm going to write down the metric form. So this is a point where I'm being more or less formal. I'm including this so that the notation is clear later on. So the metric form is defined to be this particular map. And locally, we write omega g as square root of -1 gi j bar dzi dz j bar. So here, a little bit of notation. You might have noticed I put this bar over the I, or sorry, over the j, and that's because it's referring to this anti-holomorphic coordinate. And so if, for example, I didn't include this part, you would still understand that this I refers to a dzi and this j refers to a dzj bar. So that's why that is. Okay, and now I'm going to talk about our L2 structure. So I've defined PQ forms. And now I'm going to give it an L2 structure. So L2 structure in the traditional sense is square integrable. We're going to give that meaning in our context. So we're going to take a compact complex manifold and equip it with a Hermitian Riemannian metric. Locally, we write a PQ form theta as theta I sub j bar dzi wedge dz bar j. So that's our theta. And here the capital letters refer to multi-indices. And each multi-index has, so the I has size P and the J has size Q. So it's a PQ form. And we also are taking our coefficients to satisfy a skew symmetry condition. And now we're going to define a pointwise inner product using our pointy brackets between theta and eta. Both of these are PQ forms. This is going to be our ij coefficient theta. We have these metric terms. And this is theta KL. So a little bit more notation is going on here. We have these multi-indices, but we also have raised indices on the metric. And so the raised indices refer to the inverse of the metric. And the L2 inner product now is just the integral over x of the pointwise inner product with respect to the volume form we get from our metric. And we define our L2 space to be the Hilbert space closure of smooth PQ forms on X, theta on X, such that the norm of theta is finite. So that's L2. Am I moving the screen up and down too fast, or are people able to read as I'm writing?
Emily, I have a question.
Yeah.
So on the inner product that you defined up there, so go up a bit. Is that meant to be a summation on IJK? Oh wait, hold on.
Yeah, so there's implied sums over the lower indices.
I see. Right.
Okay,
May I ask a question?
sure.
If your manifold is compact, do you really need to take the Hilbert space closure? Like, would it be fine with already?
The reason we want the Hilbert space closure is we're not interested only in studying smooth forms. So the reasoning behind that is to expand to things that aren't necessarily smooth. They aren't differentiable in that sense.
Okay, so they really are just L2, like that's maybe all you can say about them. Okay, thanks.
Yeah. Mhm. Okay, so now now we have our notion of PQ forms on a complex manifold and what it means for a PQ form to be square integrable. I'm going to talk a little bit about weak derivatives and how you define a Sobolev space, which is a space where you have some weak derivatives on a Riemannian manifold. So first, just talking about a weak derivative, you want to see what that looks like. So suppose U and V are locally integrable on a set U. For now, we're just working in Rn. And alpha is a multi-index. We say that V is the alpha-th weak partial derivative of U. So we write this as d alpha U is equal to V, provided that this holds. The integral over U of U d phi dx is equal to this expression where you'll notice we're integrating over U, but there's no differential operator on this side. So this integral where we've shifted we put the derivative on phi is equal to what would happen if we just integrated phi with this V. I don't know if that was very coherent. I apologize. So this is for all compactly supported smooth functions on U. So if this holds, this relationship holds between U and V, then we say that V is the weak partial of U. And now we can define what a Sobolev space is. So there is a more general definition, which involves other, oh my God. It involves other norms besides the L2 norm. But we want everything to be a Hilbert space, so we're just going to be talking about things which are square integrable, consists. So this is all locally summable functions U such that for each alpha such that alpha is less than or equal to A, this is again a multi-index. We need d alpha to exist weakly, so that's what we defined above. And d alpha of u is L2. All right, so some notes on this. If you take H0, this is just L2, because we're not requiring any weak derivatives in H0. We're just saying that the function is L2. Also, for each, oh, I'm very high tech, and did I just mess something up? Oh no. Undo. Okay, back to normal. Okay, so for each k, HK is a Hilbert space, and the norm on this Hilbert space is this. So we take all the multi-indices less than or equal to k, and we sum over the L2 norm of the partial or of the weak derivatives. So by the definition, we know that these weak derivatives are L2. We're summing a finite number of them. This is going to be finite as well. And that's our K norm for HK. All right, and now we're going to talk about defining Sobolev spaces on a on a complex Riemannian manifold. So you can define this. You don't need necessarily, you certainly don't need to take your manifold to be complex. I am, because I want to focus in on what happens to PQ forms, and I need that complex structure. So we're taking, oh no, I keep bumping it with my hand. Okay, so we're taking a complex Riemannian manifold M, and fixing a locally finite, oh no, locally finite open cover U sub alpha indexed over some A. I used alpha before to be a multi-index. It's not a multi-index here, it's just an index, so I apologize. If I try to change the notation now, I'll probably just confuse myself, which I don't want, so bear with me. Okay, open cover with coordinates x sub alpha and a partition of unity chi sub alpha subordinate to our cover. Okay, so for a PQ form theta, we identify the restriction of the pullback of theta by our coordinate. So we pull back theta, so theta is now in terms of coordinates in Cn. We identify this guy with a vector valued function f equal to f1 through fr. We can do this because locally this bundle is trivial. So we pick coordinates that trivialize the bundle. Once we put the form in terms of coordinates in Cn, we can write it as this function. Okay, and so now the Sobolev norm on F is defined as such. So we get this K norm is equal to the sum over our little guys. And so this is now the Sobolev norm that we're taking for our form in each chart. And we can define the Sobolev norm of our PQ form theta to be the sum over every guy in the chart. And notice that this is, because we chose our cover to be locally finite, at each point you're only summing a finite number of these terms. And okay, so now we take our Sobolev space of PQ forms to be the Hilbert space completion of smooth PQ forms with respect to this norm. Okay. Something that you might have noticed while I'm doing this is that in order to make this definition, I chose coordinates. And you might be thinking, if you change coordinates, does that mess anything up? Is this well-defined? And the answer is yes, it is well-defined. When you change coordinates, you just change to, drawer, you're muted, so.
I'm trying not to say too many things, but I don't want people to be misled. The norm changes depending on the coordinates.
Yeah.
Not only that, in this situation, it depends on the partition of unity. And it's not, doesn't give you a well-defined thing for M unless M is compact. If M is compact, you get not a single Sobolev space, but you get a different one for every partition of unity, but they're all equivalent as topological vector spaces. They're quasi-isometric. For any choice, you get one thing, but it does depend on the choice of partitions of unity. The norm does, not the space. But it doesn't matter in the end. You pick one, and you're just going to use this as a tool. This is not intended to be a God-given structure.
Yeah. So this is not canonical, but the norms that you get are all equivalent. So you get the same, HS. No matter what norm you pick, you just pick one and roll with it. Okay. And proving.
Can you repeat what is X in your notation?
Oh yeah, sorry, this should be X sub alpha. This is the coordinates we picked for each chart.
Also, capital M and capital X are always the same. So they just naturally deform one into the other.
Emily?
Yeah?
I was wondering what big K is. Is it just labeling, or does it mean anything like a compact set or something? I don't know.
Oh, here?
Yeah, sub big K, yeah.
So that refers to the number of weak partials you have. So
K
this
S also.
Huh?
K equals S also.
Yes. My notation is just all over the place, so I apologize for that. So let me put this K up here. The reason I'm using K is because I used K when defining the norm for the Sobolev space. So when I'm using the norm K, it's this norm, which we've defined for this vector valued function as the sum over the coordinates in that function. And then we can take that definition and use it to define something for our PQ form.
That makes sense. Thank you.
Okay. All right, so now we have our setting. We are studying square integrable PQ forms on X with a Hermitian Riemannian metric G, and also forms that have weak derivatives. And we're taking X to be compact, complex manifold, and G to be a Hermitian Riemannian metric. Cool. So we have our setting. This is the end of the prologue. We have 20 minutes left. Let's define our operators. Are there any questions up till this point? People have been asking questions as they come up, but we're moving on to chapter 1, so want to resolve any issues here first. Okay. So chapter 1, this is a bit of a conceit for me presenting this as chapters, but it's easier for me to think of it this way. So here we're going to meet our operators. So the first one is going to be the d bar operator. So we take theta to be a smooth PQ form, and d bar of theta acts in the following way. So we get the kth z bar derivative of our coefficient functions. We get a dz bar k, and then we have this guy, which was attached to our theta. And now you sort of push the dz bar k into the dz bar j term, and that gives you a factor of plus or minus 1. And if this is repeated, then it cancels because this is the exterior product. But for our purposes, I'm not really concerned with that. I'm not going to be writing down a whole lot of equations. I just wanted you to be able to visualize what this particular operator does, because it probably helps ground what's going on in your understanding of derivative operators. So now we're going to talk about the adjoint of d bar. That's not d bar. And we're denoting this adjoint as d bar star. Okay, so
with d bar, this is a sum where k is like from 1 to n or something.
yeah, so this is a sum over k and your indices I and j. Yeah.
So what do you mean by the indices I and j? I would have thought that those were fixed. And k is changing, but I and j, they sort of like were stationary.
I'm not really sure what you mean by stationary, but when we write theta locally as this. Where it's understood that we're summing over a bunch of different terms that have p holomorphic part and q anti-holomorphic part. So there's a sum
Okay, right.
here, and then there's a sum when you take the derivative to account for all of your k's.
Okay, I got you.
Okay. So we're taking theta to be a smooth PQ form. and we're taking eta to be smooth PQ-1 form with compact support. So formally, we compute, or we can compute the adjoint d bar star as it acts on theta by this relationship. So the inner product of d bar star theta with eta should be the inner product of theta with d bar eta. This you obtain with integration. You integrate by parts, you have compact support, things work out pretty nicely. And this is the relationship for an adjoint in the usual sense. Because we're on a compact manifold with no boundary, things have compact support, so we don't have to make any sort of extra restrictions for our setting, and this formal definition works in our case. I'm not going to compute what d bar star theta is, what the explicit expression for that is, because I'm also not going to use that expression later on. You do need it in order to do a proof of one of the statements we will see, but because I'm not proving it, I'm not going to write it down here. It's also very long and I risk confusing my audience needlessly. So we'll just leave you in the comfort of your ignorance and move on. So something I'm going to note is that as d bar acts on sections, this is a very short screen. Oh my God. So as d bar acts on sections, what it's doing is incrementing, or it acts on PQ forms, it's incrementing this Q. So you're getting one more there, and d bar star has the opposite effect. So if we act by d bar star on PQ forms, we subtract one from our Q index. Okay. Are there any questions so far? Because we're about to get a little crazy. So once we have these d bar and these d bar, this d bar star, what we want to do is define a Laplace operator. And what that's going to look like is box is equal to d bar star plus d bar star d bar. However, this is defined on smooth forms. We want something defined on L2 forms. We can, because smooth forms are dense in L2, we can just extend it maximally. The problem is that that extension will not be self-adjoint, and for purposes later on, we'll see we want that self-adjointness. If it's not obvious to you why that extension is not self-adjoint, that's fine. It's not an obvious thing, but you can come up with examples that should show to you that that's not self-adjoint. I'm not going to do that here because of time purposes. That's another little homework problem for people to show that the maximal extension of this operator is not self-adjoint. So instead, we're going to turn to a fun interlude, which is a pun, because what we're going to do is look at a functional analysis result. So this is called the Friedrichs construction. I explained this construction to Marcus, and he was very upset by it. So I'm sure that this is going to go perfectly smoothly. So we're taking a Hilbert space, H, with an inner product, which I'm just going to denote with these round brackets for now. And we're going to take a dense subspace of H. So it's dense in H, and on this D, we have another inner product. So this is an inner product on D, such that D is a Hilbert space with respect to Q. Suppose that for all x in D, we have that the norm of x, the Q norm of x, dominates the standard norm, this norm on the whole Hilbert space. Then we can find a unique self-adjoint operator F with domain sitting in D. I'm going off the screen. This is extremely messy, I apologize. Such that if you take the Q inner product of two guys in D, this is equal to F applied to X with Y for all X, Y, and D. And moreover, this equation, F of U is equal to X, has a solution for all X in your Hilbert space, your larger Hilbert space. So this is a long statement. There's a lot of setup, but the idea is you have two inner products. You want to get a self-adjoint operator such that when you take the inner product in one sense, it's equal to the inner product in the other sense with changing one of the vectors by the self-adjoint operator. Okay. So I am going to prove this because it's instructive for later on. There's some movement in the chat. Which I check. Yeah. I have 10 minutes left. I will still prove this because we kind of need it for later on. So we're taking a point in H, then the linear functional where we map Y to its inner product with X. This is for Y in D. This is continuous with respect to Q. And we can see this just by the property that we assumed Q to have, where we look at this guy. This is less than or equal to the product of the norm of X and the norm of Y, which is less than or equal to the product of the norm of X times the Q norm of Y, because Q dominates the other norm. So this shows you that this linear functional is continuous with respect to Q, and by the Rie's representation theorem, which I never spell out, and now I'm going to misspell it because I'm pressure, representation theorem. There exists an element T of X, which is in D, such that X, this inner product, is equal to Q of TXY. Okay, because our subspace D is dense in H, this is well defined. And we can also show that it is bounded. And that again comes from, so that's kind of a quick computation. So T is bounded. Yes, Rie's. T is bounded. This you just show by taking, oh my God. T, the norm of this guy, which is less than or equal to the Q norm of this guy, which is equal to, by the definition of T, X TX, which is less than or equal to X TX. So not only does this tell you that T is bounded, it also gives you an upper bound on the eigenvalue of T, and that upper bound is 1. So we'll talk about that a little bit more later on. Also, by density, T is injective, which means that you can define F equal to T inverse on T, on the image of the Hilbert space under T. And that's the F that you need in the proposition. You can prove that that is self-adjoint, which for the purposes of time, I'm not going to do because I absolutely have to get to this next part. If you want to try that, that's another thing that you can do on your own. It's not super difficult. You're just using properties of Hermitian inner products. Okay. I just stapled it backwards. Okay. So now we have the tools that we need to define the box Laplacian. I call this the box operator. So we let box be d bar star plus d bar star d bar on smooth forms. And we're going to define Q of theta and eta, where theta and eta are PQ forms, to be d bar theta, the inner product of d bar theta and d bar eta, plus the inner product of d bar star theta, d bar star eta, plus the inner product of theta and eta. And now you can see that the Q norm of theta is going to dominate the L2 norm of theta, because the L2 norm is part of our definition of Q. And now we let D, our dense subspace, be the Hilbert space extension of smooth PQ forms with respect to this Q. And now we can apply the Friedrichs construction. Friedrichs construction to get F, such that Q, theta, and eta is equal to F, theta, eta. So on smooth forms, we can use integration by parts to show that F is equal to our box operator on smooth forms plus the identity. So that just comes from, that just comes from rearranging these terms in these inner products. You move things to one side to get the adjoint, and then take the sum. So F is now self-adjoint. And we take our extension of box to a subset of L2 to be box theta is defined to be F theta minus theta for theta in the domain of F. And now, finally, this also lets us define what it means for a form to be harmonic. So our definition is, we say a form theta is harmonic if box theta is equal to 0. So if theta is in the kernel of our box operator, we say that it's harmonic. Okay, I have 2 minutes left. And in that time, I'm just going to write down the statement of the Hodge theorem because we have the tools available to us to do so. So theorem, Hodge. Let xg be a compact Hermitian complex manifold, meaning G is a Hermitian Riemannian metric. So the first is that harmonic forms, so let me add this notation, HPQ is the space of harmonic forms. Okay, so this HPQ xg is finite dimensional and consists of smooth forms. So the first part is that all of the harmonic forms are smooth. In particular, because it's finite dimensional, HPQ is closed, and we get an orthogonal projection HPQ that looks like an L, HPQ, from L2 to harmonic forms. Great. That's the first part. The second part is if we take a phi, which is L2, PQ, there exists theta in L2 such that box theta is equal to phi if and only if the orthogonal projection on phi is 0. So if and only if phi is orthogonal to harmonic forms. Further, theta is smooth if phi is, and there exists a unique solution theta sub 0 such that the harmonic projection of theta sub 0 is also 0. Okay, that's the third part, or that's the second part. And now the third part deals with the way that we invert this box operator. So the green operators, because these are operating on graded algebras, PQ acts on PQ forms, square integral Q, blah, blah, blah. And this is defined by the following. So when we restrict GPQ to harmonic forms, we just get 0. And when we compose GPQ with the identity minus the harmonic projection applied to some phi, this is defined to be the theta 0 that we set forward in the second part of this theorem. And I suppose there should be parentheses here, but I don't think it really matters. Okay, so now our claim is that GPQ is compact and commutes with our box. Moreover, d bar GPQ is equal to GPQ plus 1 d bar, and d bar star GPQ is equal to GPQ minus 1 d bar star. So we have these other commutations. And this part is what gives you the Hodge decomposition, which I'm not going to talk about. And that is the end of the prologue and chapter 1 of this talk.
All right, thank you, Emily, for giving the seminar. Since we're over time, we won't be taking questions at the end, but please join us next week to hear part 2 of this talk. Thank you, everyone.
Thank you for coming.